Hello students, welcome to the channel. Today we will see the second application of Gauss theorem, that is to find electric field intensity due to uniformly charged infinite plane sheet. You know what? We have already seen that the electric field due to point charge, how it depends with respect to distance, it is proportional to 1 by r square. When we talk about a short dipole, then electric field is proportional to 1 by r cube. When we talk about a line charge of uniform charge density, there the electric field is proportional to 1 by r. But this particular application of Gauss theorem, where we are trying to find the electric field intensity due to uniformly charged infinite plane sheet, this is a special case. And what makes it special? Yes, the exact reason for its speciality is that here we are going to conclude that E is independent. We are going to conclude that E is, electric field is independent of R. Isn't it surprising? In order to dive into the concept and how we arrive at this particular conclusion, let us concentrate on a particular figure of the plane sheet. So, can you see the plane sheet? What are the features you are able to recognize here? The plane sheet is non-conducting, then it is very thin, it is plane, means it is uniform in its thickness, and then it has surface charge density as sigma. This is surface charge density. What is surface charge density? It is the charge per unit area. It has surface charge density sigma. What is our aim? Our aim here in this situation is to find out the electric field. Where we are supposed to find the electric field? At a distance r from the sheet. We have to find electric field at a distance r from the sheet, and the sheet is non-conducting, thin, plane. It has surface charge density of sigma, charge per unit area. Now, what is the first step? Just recall, to find the electric field. Agree? It is to find a suitable Gaussian surface. We have to come to a conclusion and choose a suitable Gaussian surface in order to enclose the given charged sheet. We need a suitable Gaussian surface. So what should be? We can choose, as I told you earlier also, Gauss law simplifies complex problems by applying the principle of symmetry. We can have cylindrical, planar or spherical symmetries. So what should be the proper Gaussian surface? Let's see. So in order to find the electric field, we have arrived at a conclusion that a cylindrical surface is chosen as Gaussian surface. A cylindrical pipe-like, what you can say, structure passing through the plane charge sheet will serve the purpose of Gaussian surface. You can see in the diagram also and correlate that the plane charge sheet, it is uniformly charged with positive charge. We can even have a negatively charged sheet also. The only difference will be in the direction of electric field. If the sheet is negatively charged, the electric field will be radially inwards. But in this situation, the Gaussian surface chosen is a cylinder. You can see evidently from the diagram. And that cylinder has got again two endpoints. We will mark different parts as the end caps as 1 and 2 and the curved surface part as 3. The end caps 1 and 2 and the curved surface is marked as 3. And since we can evidently see that the electric field lines are coming out of the sheet on both the directions, so the electric field through this end cap is E, the direction is radially outwards, and the area vector for the end cap is ds, it is also outward normal. For the other end cap, the electric field is again radially outwards, or you can say the out of the particular sheet, and the surface charge, what you can say, the surface area vector is also outward normal to the end cap. So the area vector, electric field, here the angle between them is 0. Here also the electric field and area vector outward normal, their angle between them is 0. But as far as the curved surface is considered, the curved surface area, the area vector is outward normal on this side, or if we take it on this side, it is outward normal like this. And the electric field is making the angle between area vector and electric field is 90 degrees, as is evident from the diagram. If you have carefully and what you can say concentrated manner, you have taken care of the diagram, we can move on to the mathematical steps. For that you have to keep these directions in your mind. Mathematically, by now I believe you are convinced and are well acquainted with the formula that total flux is equal to the complete surface integral of E dot ds, and which is equal to Q by epsilon naught according to Gauss theorem. Phi total flux is equal to Q by epsilon naught. Now charge Q can be represented as sigma into S, which is surface charge density into the total surface area divided by the constant epsilon naught. Now this term E dot ds over the complete integral of the Gaussian surface can be written in terms of 3 parts integral. We are integrating it in 3 different parts. This is the part 1 end cap. The second part is second end cap, part 2, and the curved surface is the third part. We can call it, instead of calling it S1, S2, S3, I better mark it 1, 2, 3 so that you can identify it with the diagram here. This is for the first end cap, then this is for the second end cap, and this is for the third part, which is curved surface of the Gaussian cylinder. So the total flux phi, which is equal to E dot ds, is equal to, writing it, integration over S E dot ds is equal to, for first part you can evidently see electric field and ds vector, they are in same direction. So it becomes E dot ds becomes E ds cos 0, and that I can directly write as, for first part, I can write it as E ds. Got it? Because here the theta, angle theta is 0. E and ds are in same direction. For second part, electric field and ds vector, they are again in the same direction. Angle between them, theta, is 0. So I can write it as, for second part also, this becomes E dot ds becomes E ds cos 0. Angle between them is 0. So it becomes E ds plus, this is the integration over the complete surface, plus the third part, here we can see the angle between the electric field is in this direction, the area vector is outward normal, angle between them is 90 degrees. So this complete term vanishes, it becomes E dot ds, hence it is written as E ds cos 90, and because cos 90 is 0, the whole term vanishes. We can mark it in parts, so we will not write complete integral here, we will write it as E ds and E ds. So what are we getting here in the next term? We are getting 2 times of E ds. This is E being constant over the entire Gaussian surface. It comes out of the integral for the first part, and this becomes E ds plus, here also electric field is constant over the entire Gaussian surface. So this also comes out of the integral, and you get ds for the second part. If you remember, in the previous episodes I told you the criteria of choosing a Gaussian surface should be the electric field should be constant over the entire Gaussian surface. Now you must be getting the advantage. Since the electric field is constant, we are able to take it out of integration. So you are getting these 2 steps, and finally we can write it as phi is equal to, this is E, integration of ds, this whole surface gives you S, plus again this term E, integration of this whole term ds gives you S. We are concluding that phi is equal to 2 times Es. Moving further with the derivation of this, phi equal to 2 times. Moving further, we got phi equal to 2 times Es. Now phi can be equated to, phi we have arrived at the conclusion is equal to E dot ds, and this is equal to Q by epsilon naught. And Q by epsilon naught we will write straight away as sigma S upon epsilon naught. So phi is 2 times Es. From here we got this is equal to Q by epsilon naught, which is equal to surface charge density into surface upon epsilon naught. Here we have actually applied Gauss theorem. Here in this statement we have applied Gauss theorem here. Moving further, S gets cancelled on both the sides. What are we supposed to find out? Actually, why are we doing all this derivation? Yes, to find out the electric field. So electric field E is equal to sigma divided by this 2 comes here in the denominator, and you get 2 times of epsilon naught. Expressing it properly in vector form also, we arrived at a conclusion that the electric field E is equal to sigma upon 2 times of epsilon naught. This is the scalar form or in terms of magnitude. Do you remember at the onset of the class today, I told you that this is going to be a situation slightly different from what we have been studying earlier. Like for point charge, E is proportional to 1 by r square. For short dipole, it is proportional to 1 by r cube. For line charge, E is proportional to 1 by r. But this situation, in this situation, electric field is independent of the distance at which we are trying to find the electric field. A special case worth noting. If I want to express it in vector form, then electric field vector is equal to sigma upon 2 times of epsilon naught in the direction of r cap or n cap, whatever you have chosen as the outward normal, you can write it here. This represents the vector form of electric field due to plane sheet, infinitely thin plane sheet, uniformly charged, particular sheet which is uniformly charged. We are getting this is the result, and here the point to be noted is E is independent of the distance r at which we are trying to find the electric field. Here we conclude a small conclusion and an extension. Electric field, we concluded electric field vector is sigma upon 2 epsilon naught in the direction of outward normal to the what you can say particular sheet or plane of sheet according to its orientation. So we concluded electric field is independent of r. This is an important conclusion to be kept in mind for applications, for conceptual questions, for MCQs and other fundamental type of questions. If you are asked to plot a graph between electric field and r for this particular situation, that is for infinitely thin uniformly charged sheet, then obviously the graph is coming out to be like this. Means E is independent of r. At all values of r, E is going to remain the same. Now second important thing, what if the plane sheet has finite thickness? How will the result differ? Can you see the sheet of finite thickness? This will be considered as a sheet of finite thickness. In that situation, the electric field result will be sigma upon epsilon naught instead of sigma upon half epsilon naught or sigma upon 2 epsilon naught. Instead of having this, we will have this. Means the result actually doubles up. This is sigma upon 2 epsilon naught. We will get sigma upon epsilon naught when? In this situation. When instead of thin, you are having a sheet of finite thickness. Why are we getting this result? Because when a sheet is of finite thickness, you have to take into account charges present on both the sides of the sheet. You are adding up or you are summing up, you are taking into consideration the charges present on both the sides of the sheet, and there you get, till here we got in the previous expression also, flux is equal to 2 times Es. This we already got here. But here in this particular expression for single-sided plane sheet, we had only sigma s upon epsilon naught. But if it is like this type of sheet, plain sheet, infinitely thin, single-sided, so it will be sigma s upon epsilon naught. But if it is a sheet of finite thickness, then it will have charges on both the sides which has to be taken into account. There it becomes 2 times of sigma s upon epsilon naught, and this 2 gets cancelled, and the result is obvious. E is equal to sigma upon epsilon naught. This is something which you need to keep in your mind, and I hope you understood it. So stay connected, stay tuned in, and refer to the episodes, previous episodes if you have any doubts, and you can put your doubts in the comment section also. All the best. Thank you.